Okay. Yeah, I will repeat some basic concepts about spontaneous symmetry breaking, and how this works in the simpler version, and then we will come to our main topic of this part for the electroweak symmetry and breaking and the resulting mass spectrum of all the gate boson and the fermions. And the Higgs mechanism, or typically we say the spontaneous symmetry breaking actually acts on from the Higgs fields is like the complex fields with the real and the complex, real and the imaginary parts, and actually the potential has the local minimum, has the minimum as a physical vacuum, and actually if this expectation value of this vacuum is not non-zero, there will be resulting this spontaneous symmetry breaking. Actually, it's very clearly shown in. Okay. Oh, yeah. In this plot, when the temperature is higher or energy is higher, actually it's in the symmetry state. In this, the expectation value of these fields is 0. So in this way, we are in the symmetry phase. But when the energy is lower or the temperature of the early universe is getting lower, actually we will have the phase transition to this symmetry phase. Means there this parameter will get into the negative, and we will have the expectation value of non-zero at this typically it's at the maximum height shape of this potential. So we will get into this local value, and as I mentioned yesterday, this will be break the gauge field environment, gate environments, because this is non-zero value. Yeah, then the real part will go to the real physical Higgs fields or Higgs particles in the contrast point of view. Then the imaginary part, will go to the additional, the third component of the gauge fields, and then we will come to the physical or Higgs field with energy in this range. Actually, you can define this square root of 2 times mu as a mass, and then finally we will get the mass of the gate boson as some additional one additional longitude components. Then we can have the mass in this form. So this means we have the relation. Even in this very simpler version, the mass of gauge fields will have a direct relation with the Higgs mass. And then we can come to the real case in our world, the electron-weak symmetry breaking, and the unified theory of the weak and electromagnetic forces actually here. So it's based on it's mentioned yesterday, the SU2 times U1. Here the subscript L means it's a chiral field transformation. So we will divide the fermion into the left-handed and the right-handed, and for the U1 there will be a typical charge, means hypercharge. So in this way we can define all the quantum numbers of the fields and make the gauge transformation, and to define the physical field or physical particle of the gauge fields and also the Higgs field. Okay, here this is Higgs doublet, the only scalar in the Sun model, and there were two different components with hypercharge. We can define this, and for these Higgs fields with gauge transformation is shown this way. This is a doublet of SU2. So typically we can have the Pauli matrices times some local variable, the theta, with 3 different components, and also some additional U1 transformation. So this is the general generator of this group, 2 times U1 or the gauge invariant transformation. And also we will have the typical Higgs field for this doublet. It's just some generalization what we have mentioned yesterday. And for the fermions, firstly we can see the simply case the lepton in one generation. So this is the real model in Weinberg's paper, the model of lepton. And so the left-handed part will be the doublets, and we will only have the right-hand component of the electron. No right-hand neutrino here. So this is why neutrino will be massively seen in the initial creation of the STEM model or this electron-wave theory. So then we can define the Yukawa coupling part for this for the leptons. You can see H is a Higgs doublet we mentioned before, and L will be the doublet, and R will be the singlet. So which also include the Hermitian conjugation part to make it Hermitian electron density. So if we explain this in this way, it's very easy to show it very clearly. So when the neutron part of the Higgs field got the web, so actually we will get the mass for this electron. We will show it later. Yeah. Then we can rewrite this Higgs field to be some web times the plus the real part and the imaginary part, and also for the charged Higgs component also we write it. Here the charged part, since our vacuum is neutron, so we don't have the web for this charged Higgs part. So then we will the web of each will be in this form, yeah, as I mentioned here. So after we include this decomposition, so we will get this typical mass term of the electron according to our famous Dirac equation. You can still show here. So here we will have the Dirac particle mass term will be the Carroll form. So you can see from the left-handed to right-handed couplings. So actually here it will be the mass of the electron. So it's proportional to the V, what we define as the excitation value of the Higgs or the spontaneous symmetry breaking of the Higgs mechanism. So, and also there will be an additional coupling constant. The YE will be the usually we define as the Yukawa coupling for this particular interaction, the Yukawa interactions. So we have explained all these parts. So then we can generalize to the more complicated case for the quarks, since we have both the up and down quark have their need to have their masses. So in this way, we need to define both the doublets, for this up-down part, and also for the singlet part, the SU1 singlet part for the right-hand component. Here I already call it left-handed as a doublet, right-handed as singlet. This is for the so-called particle. For the antiparticle, it will be reverse. Yeah. And then, yeah. Also here I show this in 3 generations. So we will have the first generation fermions, second and third. So they are similar. So, and also we can define the hypercharge in some very consistent way, the so-called gamma and Sherman relation. And then we can write down the Yukawa coupling for these quarks, and both the up quark part and the down quark part. Here we also show it in 3 forms, so 3 generations, like the capital O, capital O, U, capital Q, yeah. And here we use the charge conjugation of the Higgs fields to match the invariance under the SU2 and the U1. So that is why in particular for the hypercharge isospin, yeah. So we need to use H tilde for the up quark part, and use the H as the down quark part to give the mass for example here, the U quark will have this mass term and the down quark will have this mass term after we get the wave for these Higgs fields. So again, the mass of this will be proportional to this V. Yeah, this is why Higgs gives the mass for all the fermions. So they are proportional to each other with the coupling of the Yukawa coupling. So here we also write down the Y in the capital, means it's a matrices according to different flavors. So here we need to define or to write down their physical field of these quarks to diagonalize these mass matrices and to get the final masses of all the physical quarks, and then simultaneous, and then we will get the mixing, and in the later we will show it in the charge current interaction case. Yeah, here is we write down this in the matrix form. Yeah, already showing in this diagonal term for this m heights. So already the Hermitian matrices will be decomposed to the two unitary matrix. Yeah, this is a theorem in mathematics. So we just use, for example, the up quark mass matrix will be decomposed at the left part of the unitary matrix and the right part of the unitary matrix. So for the Hermitian matrix, it can be decomposed in this way. So both for the up quark and for down quark, then we will get the diagonal form of the quark matrices, and then their eigenvalues will be their masses. Yeah, here. So now we define this in this prime part, so this will be the physical fields. And then we can come to the mixing, since now we have the several unitary matrices for the left and right, and also for the up quark and down quark. So we need to show what's their combination, or what matrix is the physical matrix to describe the quark mixing or the flavor mixing here. So yeah, we again write down the kinetic term with this is a current derivative as I shown before. Yeah, this will be the current matrices for this doublet and also for this singlet part. Yeah, and this also need to require to respect both the SU2 non-abelian gauge invariance and also the U1 case. Yeah, we need to do this before we define the mixing, because since we need to know the physical field for the gauge field, the W and D and the photons. And then we can calculate their charge and also for their hypercharge. For example, we know the charge of up quark and down quark, the fractional charges, and also we can denote the third component of isospin. Then we can use the Gauss-Schema relation. We can get the hypercharge. So this this way the doublet will be 1/3, and the up quark down quark singlet will be 4/3, and the finally down quark singlet will be the -2/3. So yeah. Then we can define or take out their kinetical term of the left-hand quark doublets. So since we have the current derivative here, so we will have the coupling between the fermion and the gauge field. Here is just the W123 and the B mu. This is the gauge field of the U1Y. It's still not the physical field. We need to define this later. So here we will have by writing down this derivative the covariant derivative, so we can have this up quark coupling to down quark with the field of W1, W2 with this is the polymatrices. And also, this is for the coupling of up quark, down quark to themselves with the third component of this SU2 gauge field, and also for the U1 gauge field. So here we will define the physical gauge field W plus minus in this form. So then we can write down these charge current interactions. Yeah. Then here we write down this particular part, and we will get this coupling in this form. So it means the down quark coupling to up quark with the W plus and vice versa with the Hermitian part. And then we can write down the chiral part of these fermions. So we will return to the famous Fermi-German V minus A interaction for this particular charge current interactions. This is proposed rather before the creation of the Stern model, but it's based on the parity violation. Yes, it's a V minus A structure. And then we will define our flavor mixing. Since here we are only talking about the interaction between quarks and the gauge fields, we need to convert to their physical basis or the mass agent states. Yeah, then this is what we have for the when you diagonalize the mass matrix, then we can write down their relation between the fields created in the Lagrangian or the doublets, and then for the height component will be the physical field with definite masses. So here we will have this 4 mixing with up down quark with and also left and right hand component. But this 4 matrix is not the physical measurement, not measurables. We need to define in our charge current case. Yeah. By the way, so this tell you why after this transformation we can get the diagonal Lagrangian for the quarks, yeah, up quark and down quarks. You can see all the masses are in the diagonal form, so they are now the physical fields and with the physical mass. Yeah, then this is the physical flavor mixing for the quarks, since they only appear in the interaction part, the charge current interaction. So this will give you the coupling with the physical D heights and U heights. So since D and U have their own coupling with the initial fields in the doublets, and then only their combination will be measurable to show their interaction strengths between the up quark, down quark with the W gauge boson. So these 3 fields or particles are all physical. So only this combination will be or can be measured in the experiment, for example, in the meson decay or other decay processes and in experiments. So this is the important point I want to mention. So here is also, yeah, this is also the famous so-called Kobayashi-Matsukawa matrices or matrix. Or you already and also Kabibo here, since he firstly created the 2x2 matrix. And as I mentioned yesterday, this Kobayashi-Matsukawa mechanism also gives you the possibility to have the matter-antimatter symmetry or the CP violation. I will show it later why this can achieve. And yeah, another point I want to stress that the flavor mixing is not only the mixing or the mixing matrix for to diagonalize the mass matrix. Actually, it's a mismatch between the interaction part, the charge current interaction here, and the mass term as Yukawa coupling. So this is because we have both the gauge coupling, gauge interactions, and the Yukawa interactions. And these two interactions are not in parallel all the time. So in this way, by definition, there should be some mismatch between these two different interactions. This is the physical origin of this the mixing, both for the quark case, the CKM matrix, and even for our later case, when we describe the lifetime flavor mixing, it's the same. Okay, yeah, how to describe this matrix is some mathematical ways or exercise. I will show it in some detail. Yeah, firstly, also we return to the 2x2 case, unitary matrix. So we can have this 2x2 with all the complex numbers. But we have the unitary conditions. So there are two modes of this. Is 1, so this will be two relations, and this is for this off diagonal part. So this will give you actually two constraints, not one. So since this component will be the complex number, so in this way we will have 4 constraints, and with this is 4 complex numbers, so will be 8. So in total we will live with 4 degree freedom or 4 parameters to describe this 2x2 matrix. Yeah, we can show in this way 1 mixing and 3. Yeah, here I also for general case we put all the phase to all the elements. So actually there will be one universal phase can be removed. And then we can write down this relation. So here is a file, but we need to use the unitary condition to make the constraint. Actually, by constraint this equation, we can remove one of the phases actually. So finally, we will still have 4. Yeah, and by some rearrangement of all these relations, because of unitary constraints, we will have, by taking out one universal phase, we will live with 3 phases. One is on the left part, and the other on the right-hand part. And but these 2 parts phase matrix are not physical observable, since we will show it later in the charge current interactions and the mass and the kinetic terms. Actually, they can have an U1 global symmetry. Actually, here is a global symmetry to show this. Yeah, so you can see this only this inner real mixing denoted by theta will be the observable in this charge current interactions. You can show here. We can insert the general case, the 3 matrices together product to these charge current interactions, but we can redefine their fields, like the U quark, charm quark, down quark. Since the S part is 1, so we only need to reabsorb these 3 phases in these Dirac fields. Since we have this freedom to make this redefinition without changing any physics, so it will be, we have the freedom of this. Actually, from physical point of view, this is because the Dirac field have the U1 global symmetry. So finally, we will have the real matrix, rotation matrix to describe the 2x2 flavor mixing or 2x2 or charge current interactions. Yeah, for 3 it will be, so because of we only have the real part, so we can conclude that there is no CP violation in the 2 flavor case, and we only need to go to generalize to 3x3, the 3 generation mixing. So this is why this Kobayashi-Matsukawa happen, or they conceive this possibility and their models. Then we can again count the free parameter in 3x3 case. I will do it not so in detail, but I will tell you some numbers. So again, we will have the 3 by 3 matrix. So since it's a complex, we will have 9 times 2, so it will be 18 real parameters. But we can remove, we can remove 9 of them by the unitary relations with 3 diagonal parts and 3 off-diagonal term part for the unitary relation. The diagonal type is the square root of the 3 element to be 1, and the off-diagonal type is the orthogonal relation of the 2 rows and the 2 columns. So this off-diagonal part will be the complex relation. So it contains 2 constraints or 2 degree freedom. So in total, the unitary relation will reduce 18 to 9. So finally, we will, for this 9 parameter and square parameter, so we will have 3 mixing and 6 phases. 3 mixing is very easy to understand. We have 3 by 3 matrix, so we will have 3 rotations to describe all the rotation in these three different directions. And but for the 6 phases, actually not all the phases are physical. For example, here I use my previous slide, so I show it in the neutrino case, but actually it's the same for the quark case. So it contains the kinetic term, the mass term, and also the interaction terms. So the mass term, also the mixing is come from the diagonalization of the mass term, so it's okay there. And the kinetic term is invariant under this unitary transformation. So only we are left with weak kinetic term, in particular for the charge current part. Charge current part, actually we again have the global phase transformation for all the Dirac fields. So the charge leptons and the neutrinos here. And then if one can insert the into the charge current interactions, you can see for these matrices, since we have all 6 phases. So one is the global phase can be eliminated, and there are 2 phases, two phases in front of the mixing, the 3 by 3 mixing, and also 2 phases on the right part. So finally, for these 6 phases, only 1 cannot be factorized out, so can be included in this mixing matrix. So this is the only physical variable in the mixing for the here I'm discussing about the quark mixing, but I show it in the lepton cases. Sorry if I used some previous slides. So for these 3 by 3 matrices, there are some standard parameterization. For example, here we assign the only complex phase together with C213 here. For example, this is also for the lepton flavor mixing. So as there are additional real rotation, so we can put this here. So this is for the Dirac cases. Since I mentioned that we have used the U1 global phase transformation, it's only applicable to the Dirac fields. So for the later neutrino as Majorana, we'll have 2 additional phases because we cannot use this transformation. By the way. Then actually, from the mathematical point of view, all the description about the unitary matrix are equivalent to each other. Only because we have some conventions about mixing angles, and we will denote some, for example, standard way to define this matrix for quark, also for the neutrino case. So usually we use this as a standard mixing. For example, there's the C213 on the right hand part, C23 on the left, and the C212 in the middle. Actually, in the neutrino case or in the neutrino oscillation, this is has some advantages because if we use C13 in the middle, actually, when this parameter goes to 0, and we can simplify the solar and atmospheric neutrino oscillation into two flavor cases. This is the tradition or the history for the neutrino oscillation studies. By the way, I mentioned this. But mathematically, actually there are 9 different, 9 or 12, I cannot remember. Yeah. Yeah, 9 probably. Sorry, I need to confirm. Probably you can tell me how many equivalent parameterization for the 3x3 matrix. Yeah, probably it's a quiz. Yeah. Yeah, for they can have different, apart from the phase convention, only the mixing. Yeah, the orders or which kind of rotation is needed. Yeah, actually there are some discussions in literatures. Okay, yeah, there are different order of this. For example, we can assign the phase difference and also the mixing. We can put C13 here or C12. All the parameterization are the same, but only if it is simpler to describe the experimental results. For example, this is why we usually use the first one as a standard one. And then I will have one homework or quiz for this. Since I will not discuss the flavor mixing for neutrinos or neutrino oscillations, I only mention about neutron mass and mass generation in a later stage. So I have one homework 3. This is a very particular special mixing pattern. Actually, probably you don't know the name of this. It's a tetra maximal. It's decomposed into 4 maximal mixing in the subspace 2x2 matrix. So finally, one can get this very special. Only use 1 and 2 and I. It's very. We even don't use 3. Yeah, for this matrix. So the work is please write down the 3 mix angles and write down the phase. What's the value for these 4 parameters? From here, I give some hints. Do not directly use it, but we have the phase freedom to decompose this the complex phase. Yeah, we can take out some additional phase matrix on the left and right part. They don't change the phasor result. So usually you can use these 4 formulas to write down this 4 different the 3 mix angles, and one phase is using the so-called Yaskok. I don't have time to introduce Yaskok in some detail, but this is so-called the rephasing invariant in the mixing, both for the quark sector and the neutrino sector. Yeah, I need to go faster since I still don't tell you what's the Z boson and the photon. Yeah, then we can write down again the kinetic part for the Higgs for the current derivative part. So here we will have the this is only I write down the mass part. You can see this is the mass of the charge gate boson, the W, and then we will have some additional term proportional to the square of this combination. So that means our physical gate boson, the neutral gate boson, the Z boson should have this combination to get their mass and to leave the photon, the physical mediator of the electromagnetic field interactions to be massless. So this is from the mass part we can guess in this way, yeah, to get a massive gate boson and a massless photon. Yeah, then we can see it clearly to this part. You can see by write down the couplings G plus and G. One is for the SU2 and another is for the U1 and gate coupling. So this is the third component of this SU2, and B is field for the U1. So after we diagonalize this matrix, since it's rank 0, rank 1 matrix, so we can write down this only leave with two elements to be non-zero. So then we will get firstly the physical field for this A and Z. This is, since there's no mixing now, and also we can read from the matrix that the 1 element is 0. That means our photon is still the massless particle. So then to convert this matrix to this physical coupling matrix, so we will have the additional 2x2 mixing matrix, or when mixing angle, the theta W means it's weak, or Weinberg, So in this way, this mixing angle is defined in this way: the strings, the difference of strings, or strings ratio of the strings. So then we can also have the mass of the coupling of in front of the mass term, So we will have this the G squared plus G prime squared. So this will be the mass of the Xeon. So actually, you can see now the mass of the neutron gauge boson, the weak gauge boson, and the charged ones are different, but they have a very particular relation with each other. Together with the parameter of this the weak mix angle. Then we can have these neutral current interactions. We can recall this kinetic term, but the quark interaction with the additional gauge field, and we can rewrite this to return to the physical fields. Then we can have this left-hand part, the up quark coupling, down quark coupling with there's still no physical field. We will rewrite this by the rotation, and we can get the coupling with, for example, the left-hand up quark, down quark, and also the right-hand part. So here, their coupling constant will be, in this way, will only depend on the G parameter, but in the physical case, they will have difference. Here we can return to from the Lagrangian field, the B and the W, to the physical fields, the A and Z. So in this way, we can make this subtraction, and then finally we can get this. For example, for the coupling with photon, or this is electromagnetic interactions, is a famous U1 case we have mentioned yesterday. So they are vector coupling with the fermion, and the A mu. So this is a simple vector interaction. But for the Z case, here is also the vector case, but with some different parameters. This parameter can be calculated with the third component of their isospin, and also for example, the charge of this, and also the weak mix angle. They can universally write in this way, denoted CF as the coupling of this Z boson interaction, or the neutral current interactions. Actually, this is the unique prediction of this Sun model, and actually in 1973 or 2 or 3, in the Gagg-Miller experiment, they finally proved it to be existent. Okay, this is a table to write down all these couplings in the final column. You can see all this in this form, but here we don't show for there's no right-hand neutrino here. So if it is, so what's their coupling with neutral current fields, for example, with Z boson? Actually, for sure, it's 0, since the right-hand neutrino have no Sun model or non-trivial couplings. But you can write down from the very beginning, use the same formalism. Yeah. Again, if we want to show the leptonic part, since in the model we don't have neutrino mass and we don't have the red neutrino components, so it's much simpler compared to the quark case, since we only have this charge current interaction with the neutrino and the charged leptons, and for the neutral current interactions, it's also shown this way. Yeah, for this neutrino, and this is fermion, and this is a red hand component. Yeah. Then I will, as I promised in the very beginning of my presentation, I want you to calculate the cross section of the neutrino and the electron scattering. This is, you can either choose the E plus minus to muon pair or to choose this one. Yeah, this is, I want to use this as a homework since I always use this in my courses. Since if we neglect the mass of the electron, actually it's very much simpler to make this calculation since all the four particles are massless. Yeah, it's very easy to make calculation. And another point is their Feynman diagram for the electron neutrino, for the electron antineutrino, and for the muon and tau neutrino are very different, actually. Since, for example, the muon and tau neutrino only have the neutral current interaction with the electron. This is what the Geiger experiment measures. And also, if for the electron neutrino, actually, there will be the charge current interactions for the neutrino and the electron, but they are in different form for left-handed neutrino and a right-handed antineutrino. So this is a very good exercise to know the structure of the chiral field and also how to make this simpler calculation for the spinors, actually, yeah. And also for application, this is very important. For example, the electron, the cross-section of the electron neutrino and the muon tau neutrino has a ratio of around 6 to 7. So this will means if we measure the solar neutrino in the lab using the electron scattering process, we are not only sensitive to the electron neutrino, but also sensitive to the muon and tau neutrino. Actually, this is one way to test the solar neutrino problem. I think Liang Jian probably will mention this in his lecture. Oh, finally, I will come to my, probably most of you are mostly interested in this. What's the possibility to go beyond this? Since all my previous materials are the standard material in the textbook, and now it's still the existing literatures, but I just summarize. Firstly, we all want to go beyond STEM model. We want to go to find new physics. But before this, I would like to say the model is extremely successful in many different aspects. From the collider physics, actually, there are already very detailed testing about the model. All the couplings with, as I mentioned, with fermions, with gate boson, all the interactions had been measured in very accurate case. Actually, I show two plots. One is from the Atlas, and the other is from CMS. Actually, CMS is very simple to recognize. They are the coupling with particle mass and their Yukawa coupling. So that means the ratio of this will be the wave, the expected value of the Higgs. And this is, for the Atlas plot, they show the coupling both to the fermions, this is the Yukawa coupling, and also the coupling to the, from Higgs to the gate boson, from the gamma, photon, the gamma to the Z and the W. So all these coupling, they normalize to 1 to the STEM model prediction and what their data tells. So this is what this plot shows. So for example, different channels have different precision, but they all agree in this 1-1 point. That means they are consistent with the STEM model prediction. Yeah. So that means we have tested the same model prediction in all the aspects, and up to now, almost no evidence of this. But I say it's almost no because I summarized some of the drawbacks or some of the evidence of we need to go beyond standard model. This is it's only the partial list, non-elaborated. So I divided them to be two. One is some theoretical argument. For example, there's no gravity in the standard model. So, and also we still use 3 different couplings to describe this electron weak and the strong interactions. So actually, there's no real unification of this gauge coupling of the interaction strengths. So I will come back to this later by introduce some ideas about Grant unification theory. And then there are many different theoretical arguments why we need to go beyond standard model. For example, the hierarchy problem of this Higgs mass, and also in other words, they call it a naturalist problem. And also, in the related case, there will be the fermion mass hierarchy problem, since we have the top quark mass and the electron mass and even the neutrino mass is extremely small. So they have a huge hierarchy in around 11 to 12 orders. So that means we need some explanation of these hierarchy problems. And also, Jianlei mentioned yesterday the strong CP problem also. We need to explain it, no matter it's from the axion or other dynamical solutions. Yeah, and for the experimental case, actually I listed some of them. For example, there's no neutrino mass, we know, and we know how to add the mass, but we don't know which one is correct actually. And also, from some observation of the both from the cosmology and from the Big Bang nucleosynthesis, we know there's only matter rather than antimatter in our visible universe. So we need to explain why we only have matter, or what's matter come from, or how to explain the matter-antimatter symmetry in the universe. This is very important task to go beyond standard model. Actually, we have the evidence, we only have the matter in the visible universe. But I don't have time to cover this. If you have questions, we can discuss in some detail. And also, I think Jianlei mentioned that there's no room for dark matter, dark energy, and this is one important reason why we need to go beyond standard model. But in the following 30 or 25 minutes, I will only choose 2 of them. One is unification of the coupling or unification theory. Another is for sure I will tell you about the neutrino mass. Yeah, the grand unification. Yeah, this is the dream of why we're doing physics and why we're doing. We want to use simpler way to describe the forces. We want to unify different forces. The electricity and magnetism, unify the electromagnetism, electromagnetic interactions, and also we have the weak interactions from the beta decay, and then finally we have the unified electron weak theory by using the gauge field and also the Higgs mechanism to describe the small symmetry breaking. But actually, this is not a real unification, since we still use not a single Lie group to describe this. We still have 2, so that means we will have 2 different couplings. Actually, this is one way we want to make the unification. And also, we still need to unify both the strong and electron weak forces. So this will go to the so-called Grant unification. Yeah, starting from 1970s. Actually, this Grant unification still cannot include gravity here, since it's how the conflict between this quantum field theory and also the general relativities. Yeah, so I will only talk about this. So we want to unify the weak force, the electromagnetic force, and the strong force. For sure, there will be, to make it in some consistent way, actually we need some additional piece of, this is our price to make the unification. And also, this is our way, our possibility to test this model. We need some new integrant into this, and this is our new physics in particular. We want to test this unification theory. Yeah, what to unify? Since we want to make the unification, so first I mentioned in the standard model, I discussed in most of our time. So we have 3 different gauge fields, and 3 different gauge couplings. So we want to make it unification in some sense. The 3 coupling will go to 1. This is one aspect of unification. Another is, we want to unify the matter in some much simpler way. Now we have assigned the quarks, the leptons, and the left part and the right part in very special or very strange way to make the STEM model works. So probably some of you already have this in your minds, why it's assigned in this way. It's very special, but also very complicated. So we want to make it simpler and in some more general or unified way. For example, for this STEM model, we have 3 dimensions for 3 different groups, and they are organized in different ways. For the right and the left hand, the leptons, for the right hand down quark, up quark, and for the left part doublets. So they have very different hypercharge. So we want to unify this. So for the unification, usually we need to consider all the 3 aspects: unification of symmetry, one single group, or some simpler groups. And unification of the coupling and the unification, there are field assignments to make it in a unified way. Yeah, the first idea about the GUTS, the grand unification theory, actually is not a real unification theory, but they have the spirit of the unified lepton and quark, lepton and hadrons. So this is the so-called Partisalam. Yeah, it's in 1973 and 1974. It's 422. Yeah, it's adds the lepton as a 4th component of the QCD. So that means the QCD has 3 components, 3 different colors. But when adds the leptons, since lepton there's no color, so you can add the lepton number as the 4th color. So this is the idea of the Partisalam, and then to make it symmetry, they also add the right-hand part as the chiral, so-called to explain actually the spontaneous breaking of the parity violation. So you're using the left and the right both as SU2 doublet case. So this is the idea of the G44. So you can see now the field assignment looks very, very structured, have very simpler ways to make these arrangements. Yeah, this is, I don't want to go much details, but only some ideas. So the real unification in the spirit of I just mentioned 3 different aspects of the unification is a George-Glacial model of the SU5. So SU5 is very simpler. So since we know SU3, SU2, and U1 as our model, so the most simple one single group will be the SU5. So this is why they want to do it in this way. Actually, they make this all the left-handed fields in a so-called 10-dimensional representative. This is a conjunct representation of the SU5, and they assigned all the I think the left-hand part to be the basic representation. And they also add the Higgses in some 5, 45, and 24. This different representation of the Higgs fields to make the Yukawa coupling works to make all the prediction consistent with the model. So this is a real and the first gas model, and this is the so-called SU5. But SU5 cannot have the right-hand neutrino here. So since you can see for different colors of the up and down quark, you can show 10 times 5 is 15. But if we have 3 colors for the quarks, for one generation of quarks, one generation quarks, so we have 2 flavors and 3 colors. So this means you can see up, 1, 2, 3, down, 1, 2, 3. But we have also the left and the right-handed. So we have 12. Then for these leptons, we have the left-handed electron and right-hand electron and the left-hand neutrinos. So in total, we will have 15 fermion fields in the degree freedom way. So we separate both left-handed and right-handed. So that means in total, we will have this 15 fields assignment without a right-hand neutrino. So in this way, in order to get a neutrino mass, we need some other ways to make this. For example, we need some Higgs field to act as I mentioned, not the type 1 seesaw mechanism to require the right-hand neutrino, but use some, for example, type 2 seesaw to give the neutrino mass. And another more unified way, if you want to add the right-hand neutrino in the player, and in this way, one need to add some additional component to form the 16 component of this a single group. So SO10 is an ideal candidate for this. This is proposed by Fritsch and Peter Minkowski in 1975. This is SO10 GATT. So this is most studied GATT theory, since it has, in many aspects, it has some advantages. For example, it will have the seesaw, both type 1 type 2 insights, and also have other advantages, since now we really assign all our matter fields 16 components in one representation. So this is the advantage of this. Since even in SO5, we need to assign our matter field in 2 different representations. So in this way, we will have very good properties, and also this will include both SO5 and Partisalam as its a subgroup. So in this way, we can breaking the SO10 into some intermediate state, intermediate case, to include SO5 or even 244 Partisalam model in the intermediate state to get more reliable predictions. Yeah, and also there are some more different realization even for the SO5, the non-minimal case, and some flip case, or even with some additional U1 gauge field in together to have different reasons. And there are many different studies in last 40 years for the so-called phenomenology of this gas theory to explain different ways. The second part, as long as we have this gauge fields, the one single group, and assignment of the fields, then we can calculate the running of this. Actually, for running of this, we don't need this. We can run from the low energy part to the high energy part. But only with the standard model towards a single unification. Actually, up to now, is not realistic. It cannot be achieved without any additional components. I mean, I will show it later. So since as more and more precise measurement of the electron-weak precision observables, actually, all the running of this is a base function differential equation, and here T is a running magnitude or the energy scale of this, and you can calculate the running of the three different coupling constants. For here is the QED or the U1, and the alpha 2L is the left hand part of the SU2, and alpha 3 is QCD coupling. So here we show the inverse of this coupling. So it means this two going up means this is asymptotic freedom. Since both of these are the non-Abelian gauge fields, so gauge group coupling. So this means we need them to go up, and for the U1 it's a Abelian case, so it will be going down. So from this aspect, if we only know this part, actually it seems they might go together in some higher energies. But as all these parameters, for example, they have this BI or some couplings of this derivative, actually depends on many different factors, the couplings or some, this will be constrained by using the electron-weak precision observables. So as this going to much precise manner, the current way, they cannot be meet to one single point. This is the current status of the IgE running of these three couplings. Actually, this was studied around 30 years ago by several different groups, almost at the same time. I think one I shown it by the Ngaka and Minxin Luo, and also there are some other two additional groups. One is Calodronti with C.W. King, and the third is, I think, is some Italian groups. All three groups study the running of this. They cannot be meet together within the same model, but with SUSY, yeah, it's shown in this plot with SUSY, actually they can meet together. This is for the unification of the coupling. But we can, even without SUSY, we can make it into one point by adding some intermediate effect. Since for this straight line, this means there's nothing between our same model, the SU3, SU2, SU1, up to the grand unification energy scale. There's no new particles, no other threshold effect, spontaneous breaking effect. That means why this is in this straight line means this coupling keeps the same. But usually it's not the case, since we will have the new degree freedom open up, and also there might be some spontaneous breaking in the intermediate state scales. So this is one, for example, one example of if there is some unification, for example here, and then to the Patisalam, and then to the same model, actually there will be the threshold effect to give you some more freedom to tuning the running of the coupling constant. So finally, you can get this unification for the three coupling to one point. This is our goal. But we don't know what's inside this intermediate state, since the form of this breaking and the scale of this breaking are still unknown. We don't know where it is and how this happens. So this gives us the freedom to tuning this, and finally we can get this unification scale in one point. This is unification. Then one would like to ask how to test this. How to test this means, since we know in most of cases the unification scale is always usually called a gut scale, is intended to 10 to 15 GeV. Yeah, this is a super high skill one cannot get in our achievable way, or even I think somebody can say that if we can build a collider near the equator of the Earth, and what's the limit of this energy, probably still not enough to get this gas scale. So we need some indirect way to test this, and the most promising way is the proton decay or nucleon decay in general, to have the baryon number violation processes. Since in the STEM model, in the perturbative way, proton is stable, as I mentioned yesterday. Yeah, proton is stable since it's the lightest baryon, yeah, made of the first generation quarks. But if we have the gas theory or grand unification, so we have the unification of the quarks and leptons, so they are in the same representation. So then proton will not be stable and will go to some lighter particles, for example meson and some leptons. And yeah, here are two popular ways. One is pi0 plus the positron, and the other is the kaon and the antineutrino. So both of these have been searched in large underground experiment, in particular the neutrino experiment. And for example, this pi0 E plus is very advantage in some ultra-Cherenkov detectors, since all the pi0 and positron will have very clear Cherenkov rings for different patterns. Yeah, for both the positron and the pi0, and they have the collinear, the gamma, and then there will be some very special pattern for this. And also for the kaon decay, actually in the synthetic detector, for example, the Juno have very advantage to measure both the energy of the kinetic energy of the kaon before its decay, and the energy of the muon, and then the energy of the Michel electron. So it's a very special or very unique signature. So it can be tested in the very large detector if we have enough amount of the protons in the detector. So actually there are still some Chinese words, but I think you don't need to read this. And some other channels, but replace the meson and the lepton. Yeah. By the way, actually this kind of channel still reserve the B-L as a good quantum number. So that means for both of and this, we still have the B-L symmetry. So this is usually the case for most of the gas theory. So that's why usually people want to search for this kind of processes. But without B-L, actually, one can do this, but it will be some other strange or complicated gauge theory can achieve that kind of B-L breaking. Okay, yeah, I still don't have some time. I think proton decay was first searched just even before the neutrino experiment in late 1970s or early 1980s. The Kamikanda experiment was designed for this goal. This is the Kabuka nucleon decay experiment, the Kamikanda. So this is proposed by the Kushiba-san to build this detector. Use some giant amount of the water, since it's cheap, and so to search for the nucleon decay. But later stage, since the solar neutrino problem and the supernova 1987A observation actually makes this kind of large underground detector is mostly suitable for neutrino experiment. So later it goes to Kamikanda 2, Super Kamikanda by Tsuka and Kajita-san, and also then the future hyper Kamikanda experiment. And for other stage, other technology, for example, there will be the Juno and also Dune for the liquid argon detectors, and even future, for example, they have some ideas to combine the water and the scintillator technology, the CR for water-based scintillator detector. So most of these, they have the kiloton or even larger detector. So this will give us the sensitivity for the lifetime of the proton up to 10 to 34 and even 35. So this is the limit, almost the limit of some popular gas theory prediction. So that means we can rule out a large amount of models of the gas theory if it cannot be observed in the next generation experiments. Yeah, this is the end of my the gas theory, but for the neutrino oscillation, I think later and even the first day there are already some discussion, but I will skip the neutrino oscillation, but only mention some of the neutrino mass generation as another evidence for the new physics beyond STEM model, since as my presentation title indicates. So all the different aspects or different experiments has revealed that neutrino do oscillate from the solar, from the atmospheric neutrino oscillation, and even the man-made reactor and the long baseline celestial neutrino oscillations. So for different channels, electron, to muon to tau, even to tau neutrino, it's rather challenging, but still achieved in opera experiments. So all the experiments indicate neutrino do oscillate. So that means we need the new physics. We need the neutrino mass. Yeah. So this is the current status of this global field. So all the parameters has been measured in very accurate way. The only remaining part is we still don't know the CP violating phase. We don't know the sign of the one of the mass splitting, the so-called mass ordering, and also the octant of state 2-3 is still not determined. By the way, besides the oscillation, the absolute neutrino mass still needs to be resolved. We don't know. We only know the upper limit of the mass less than 0.4 or point something electron volt, but we don't know the absolute scale of this. So all this indicates that neutrino are massive, and but the origin of the neutrino mass is still mystery. So this is also a strong, from the experimental point of view, is a strong evidence that we need to go beyond STEM model to search for the new physics, to how this neutrino mass is generated. Yes, in STEM model, we have the massless neutrino. We will go back to the STEM model assignment. You can see we don't have the right-hand counterpart of the neutrino, but only have this for the charge absence. This is why we don't have this the Dirac mass term for neutrino, and yeah, and also for if one would like to say, if can we make a Majorana neutrino term only use the left-handed component of the neutrino, for example here, since if neutrino is Majorana, and we can get a right-hand neutrino field by using the left-hand field. That's the charge conjugation of this right-hand. It will be the right-hand component. So can we do it in this way? But I will show it in the next page. It cannot be done because now the left-handed neutrino field is in the weak doublet. So that means all this will be go together to reserve the gate invariance. So we cannot get this without any effect on the electron. So but we can achieve this if we can extend the Higgs sector to have the, for example, Higgs triplet. So we get the conclusion that the neutrino are massless in this, and it's still okay when Steenweinberg makes this model in 1967, or even until the neutrino observation itself it's established in 1998. So this is a problem, and we need to know the reason for this. Yeah, as I mentioned, we can just add this right-hand component and make the star model seems more symmetry or more beautiful, since all these components are assigned in the universal way. So we will have this Dirac mass term, and by using the standard Higgs mechanism, we can get this neutrino mass with some web of the Higgs fields and with additional Yukawa coupling of the neutrino. But we don't know the size of the neutrino. But there will be some problem for this case. Since this, the Majorana term, mass term of the right-hand neutrino, not as we mentioned for the left-hand component, we cannot get the Majorana term for the left-handed component, but we can do it for the right component. Since we can calculate the hypercharge of this, and it's a trivial one, it's 1. So that means it will have no interaction with W, Z, and the photon. So it's a totally singlet of star model gauge fields. So so this term is in all aspects will respect the gauge invariance. So this term is okay, but it will violate the left number. Well, I will show it later in the next page. So if we want to only have the Dirac neutrino mass, we need to have some way to forbid this term to happen. For example, using some symmetry. So if we use some left number as symmetry, we can achieve this. But it's still not attractive, since for this Yukawa coupling is much smaller compared to the top quark mass. This is a problem from the naive thinking, why we cannot just add the right-hand neutrino to have the Dirac mass. So then we cannot have good way to forbid this Majorana term of the right-hand neutrino. So we will add this term. So this will be, this term is not responsible. Okay, thank you. 10 minutes. I can stop at some stage and then for the questions, since this I think is much simpler. So by adding this, actually we will have this both the Dirac mass term and the Majorana mass term. So this term will, since we have both the right-hand component and the charge integration of this in the mass term. So since they have different length number, so this means process is mediated by this term will violate the left number by 2 units. So a Majorana mass term for the right-hand neutrino, or I will show it, it will be the foundation of the seesaw mechanism, will be rather new physics beyond star model. It cannot be achieved with star model fields. Yeah, this is some details of why we don't have the Majorana neutrino mass term for the left-hand field, since they have in the doublet case. So finally, we need some hypercharge 2 Higgs triplet to have this gauge invariance way. So this is, I will skip this, and I will tell you about this. I think most people want to know some details about the seesaw mechanism. So if we have the Dirac mass term for the usual case for the left and right-hand neutrino, and also have the Majorana mass term for the right-hand neutrino, this is a singlet of the model. So we can have this. By combining these two terms together, we will have this form of this. And if since the right-hand neutrino mass term is arbitrary, so it can be much heavier than the electron weak scale. So if it's much higher, actually we will have the famous seesaw mechanism to achieve the left-hand. By diagonalize this mass matrix, we will have the mass of left-hand neutrinos. So it will be inverse inversely proportional to the mass of the red and neutrinos. So this means if we have a super heavy right hand neutrino, we will have a super light left hand neutrino. This is a spirit of the Caesar mechanism. So this the scale of the mass term will be almost a little bit less than gas theory, but it's much higher energy scale. So this is the type 1 Caesar, but as I mentioned, there will be some other version of the Caesar mechanism with similar spirit, but for example, with the Higgs triplet or fermion triplet, all give similar way to have a tiny neutrino mass. This is for sure is a much studied direction for the new physics beyond the model for how to get the Majorana neutrino mass, or and also in general how to explain the neutrino mass generation. So this is another way to Also, one can see this in some effective theory spirit. The only dimension 5 operator by using the stem model field and stem model gauge invariance, and it's the Majorana neutrino mass. Actually, it's amazing since this was first written down by Steve Weinberg in 1979. And I think I have a homework, but you can check the gauge invariance of this operator and try to prove why it's unique. Then my final page is how to test the Majorana nature of the neutrino mass. I think Liang Jian for sure will cover this topic, but I only mentioned the only promising way is to do the neutrino-less double beta decay by different isotopes. This is also for sure to test the Majorana nature, the Lipton number violation, and finally the neutrino mass generation. Okay, this is my final slide. Thank you for your attention. I will keep here. Okay.
Okay, so time for questions. Any questions?
Thank you for your speech. I have a question. About matches of mass quarks,
Okay. Very early state, yeah? You mean quark mass?
Yeah. I have a question about it. This is quark mass. Are the masses of any upper and lower quarks, or they are two components of the total mass?
You mean this? You mean these values? Yeah, it's a quark of each flavor. Yeah. Up quark, down, charm quark, top quark, and the other down type.
Not total.
Not total. The individual quark mass.
Matches of mu is for upper?
Yeah, you mean for up quark. Yeah.
Yes, thank you.
Okay.
Okay, maybe 2 or 3 more. We don't have much time.
Yeah, thank you for your lecture. So I have 2 questions. Have a Higgs boson the same law for the mixing?
What?
Have a Higgs boson the same law for the mixing, or it is different from gauge boson?
You mean for the mixing or for the fermion flavor mixing? Yeah.
Yeah.
So here we only have one single Higgs, so it will coupling to all the fermions. The flavor mixing and the mass hierarchy will only determined by the Yukawa couplings. Actually, this is also a problem of the STEM model. In the Yukawa sector, we have so many parameters to get both the fermion mass, as just mentioned, the quark mass, the lepton mass, and also the mixings. All this is generated from the arbitrary Yukawa coupling matrices, and their coupling to the Higgs is all the same, the expectation value of this. Yeah.
Yeah, thank you. And the second question is, do we have a restriction of quantity quarks in system to calculate the mixed flavor, like free body problem or something?
Oh, so to use what?
Do we have a restriction of quantity quarks in system to calculate the mixed flavor?
Quantize the quarks? You mean the charge quantization? So now in the STEM model, the charges of the charge of quarks leptons are put by hand. But actually, the charge quantization, for example, why the electron have -1, actually they have theoretical or argument or theoretical reasons. For example, how to explain the quantization of the charges. Since the charge quantization actually relates to the QED and also in the model in general, how to assign their charges, or in general the hypercharge actually. Since the charge actually in the model are included in the hypercharge and together with their atom spins. So actually the hypercharge is quantized in the U1, and actually why this, for example, the electron charge of the electron is unit 1, actually there are some reasons, but I think it's not explained in the SEM model itself. Yeah, this is my answer.
Okay, maybe one final question.
Okay,
yeah.
Thanks for your lecture. I have two questions. So the first one is that Ewing's standard model can't explain the mass hierarchy problem.
Cannot. You mean fermion or?
Fermion, quarks.
No. I think this is put on by hand. Yeah, to all included. I just explained in the Yukawa coupling. So we need to admit the Yukawa coupling. Some is in the order of 1 for top quark, but for the electron it will be in the level of 10 to minus 6 for the electron mass, since there have large hierarchy between these different fermions. But the ratio to the coupling to the Higgs is the same. It will be the web V. So that means we need to put this hierarchy by hand in the coupling constant. So that means we need some very tiny number in the model itself to explain the fermion mass hierarchy. Actually, how to explain this? There are many different realizations. For example, we can put some additional U1 charge to add some hierarchical part, some power of the small parameters to explain the hierarchy. For example, the Frege-van-Nissen mechanism, and for example, this is one popular way to explain the fermion mass hierarchy. Yeah.
Okay, so in standard model, it's just used free parameters.
To fix the data. Yeah.
Okay. And the second is that you mentioned in SO10 gas.
Okay.
It includes seesaw mechanism type 2. You mentioned that but in seesaw mechanism type 2 there is a Higgs triplet. It is a new Higgs or it substitutes the original?
Yeah, I think when I'm talking about type 1, type 2, it's some bottom-up methods. We only add some integrant, reactant neutrino or Higgs triplet to minimize, realize this, make them. Actually, if you see the SO10, actually there is a large amount of the Higgs fields. I think both I think here, since we have the reactant neutrino field, so we for sure we can get a type 1 seesaw mechanism. And for type 2, we can assign some of the component of Higgs. For example, high representation of the Higgs, they can, after the spontaneous breaking, they will have the triplet part of the Higgs. So this will play a role for the type 2 seesaw.
Okay, so it means that in SO10
we already have this component from bottom-up method, from up-down methods, from top-down method by the high representation of the Higgs.